Okay, so the last immune system video here. This last section is all about, actually the last two sections. This first one is about tissue transplantation and blood transfusions, and then the last part is about diseases that occur. So that's with the immune system. So the immune system can wage war against cells from other individuals. So if you have another individual's cells put into your body and those antigens aren't the same as your antigens, then your immune system's going to launch an attack against it. So an example of this is with transplanted tissues. Transplanted tissues are usually destroyed by the recipient's immune system unless you can get a really good match where then your immune system would not recognize those tissues as foreign. And so we're going to look at that down here with tissues and organ transplants. MHC molecules stimulate rejection of tissue grafts. That means that you take let's say like a skin graft where you take a piece of skin maybe from somebody else and put it on another person, like a burn victim or something like that. And organ transplants. And if you remember MHC molecules are the special classes of molecules that display the antigens, and so that's what MHC, and no two individuals are alike unless you're identical twins. Molecules are identical. Except, as I said, with the exception of identical twins, because your DNA is identical. So therefore, when you get, let's say, an organ from another person, what they try to do is match those MHC molecules as closely as possible so that you have a greater or lesser chance of your immune system recognizing those as foreign, and because those are embedded in the membrane and of all your cells, and therefore won't launch an immune system attack. So the chances of successful transplantation increase if donor and recipient MHC tissue types are well matched. So therefore, these tissues have to be very close. And so what happens is when they find a well-matched person, usually for organ transplants, that person that you're getting the organ from has passed away, and they test those MHC molecules on that. Let's say, for instance, my neighbor last year, it hasn't even been a year yet, he got a liver transplant. And so he was on the liver transplant list, and they had tested his MHC molecules, so they have that already, that data. And then when a person passes away and they have signed up to donate their organs, then they test to see and look at those MHC molecules to look for the best match and give it to the best match on the list. And so therefore he got a liver transplant. But this third bullet, what happens is they give them, I think he had to take like almost 40 pills a day, because they give you immunosuppressive drugs. These guys suppress the immune system, so it reduces the chance of rejection, but then it also increases your risk of getting sick by something else because it's suppressing your immune system. So therefore, like for instance, they won't go out you're recovering anyway, but you kind of reduce your exposure to pathogens, and so therefore reduce your exposure to people while you are recovering from that, and he's got to continually take these immunosuppressive drugs, all right, to suppress his immune system. So, and that's always, you have to minimize the rejection there. All right, so that's what that part is. Another thing is with blood transfusions. So up here, antigens on red blood cells determine whether a person has type A, B, AB, or O blood. And what happens is you have antibodies to non-self blood types. So if you have type A blood, you have antibodies against B and AB. So transfusion with incompatible blood leads to destruction of the transfused cells. And so if we look here at this chart, so blood groups that can and cannot be safely combined in transfusion. So blood type A, it says the recipient's blood group. So they have, as it says here, antibodies against B. And so people with blood type A, what happens is they have antigen A on their surface of their red blood cells. So if we make another, this is your blood type, another chart here, and this is the red blood cell surface. RBC is red blood cell surface, or the antigen. So if you have, that's supposed to be blood type. If you have blood type A, your red blood cells have antigens of a specific shape. So they have A antigens. B blood has B antigens. AB has both A and B antigens. And O has none of those antigens on them. And so this is important to understand this chart here. So people with A have antibodies against B. So they have antibodies that will fit into this shape here. So anybody who has the B antigen, you cannot give that blood to an A person. So therefore, you cannot put B blood into A blood or AB blood into A blood person because of those B antigens. My question is now, could you put O blood into an A blood person? Absolutely, because there are no antigens on there that the A blood person is going to recognize as foreign. So if you look at this chart, this negative means, look at here, it's the presence or absence of a transfusion reaction. And so there's negative here and negative here, meaning that type A blood, you're not going to get a reaction if you give them other A blood or O blood. But if you give them B or AB blood, that positive means that there is going to be a reaction. Their antibodies are going to attack that, and so you're going to have a transfusion reaction. So then, if we just look at here and not look at B blood looks like this. B blood has antibodies against A, and so therefore anything with an A antigen you cannot give to a B blood person. So you can't give them A or AB, but you can give them B and O. And so therefore B blood has antibodies against A, and you don't have a reaction, which means you can give them B blood and O blood, but there is a reaction with A and AB blood. And then AB, look at AB. AB has both A and B antigens on it, so therefore you can give them A blood, and they won't recognize it as foreign, B blood, AB, or O. So if you notice here that they have a negative across the board, well, that means because they have no antibodies against A or B because they have both antibodies on their, or both antigens on their red blood cell surface. And lastly, O you can't give A, B, or AB because O is not going to recognize all of those as foreign. So that means they have antibodies against A and B, so A and anti-B. And so the only type of blood where you're not going to get a reaction is other O blood. So that's what that means. Now, what's one other thing that you know about red blood cells, not red blood cells, about blood type? What do you always hear with not only A, B, and O, but you also hear what? Positive and negative, right? That is called, a red blood cell antigen called the Rh factor. creates difficulties when an Rh negative mother carries successive Rh positive fetuses. I'm going to talk about that in just a second. Before I want to talk about the Rh factor. So the Rh factor is, if we look at, make another chart here, and so we have Rh and the red blood cell surface. So for Rh, that's either positive or negative. This is controlled by another set of genes. So there is an Rh antigen. So let's say here's your red blood cell. I'm going to make a different shape. I'm going to make a square shape. So that's the Rh. So Rh positive means you have the Rh antigen. Rh negative means that you do not have the Rh antigen. And so therefore, this is another factor to take into consideration. So really the only blood type that doesn't have anything on the surface is O negative, because O positive, so if you were O positive, it would look like this. All right, so you would have that Rh factor on there. A negative person does not have that. And so notice here it says red blood cell antigens called the Rh factor create difficulties when an Rh negative mother carries successive Rh positive fetuses. What happens is during delivery, if you are an Rh negative mother, so you don't have the Rh antigen, and your baby does, let's say your spouse is positive and that passes on that gene to your baby, so your baby has that antigen on there. What happens is during delivery, some red blood cells can cross the placenta and get into your bloodstream. If your baby's blood has these antigens on it, guess what? Your immune system is going to attack those red blood cells, and that's not going to be a big deal at first for this pregnancy, but what's going to happen is you're going to make memory cells, and those memory cells, if you have an Rh positive baby, let's say a couple years from then, and those red blood cells, red blood cells cross the surface, those memory cells are going to kick in, make antibodies. The antibodies cross the placenta into the baby's bloodstream and therefore will start destroying the baby's red blood cells. So it can be a really big deal. And so if somebody is an Rh negative mother, what they do is they inject you with antibodies previously, and so therefore, if any of the red blood cells, your first baby's red blood cells get into your bloodstream, you already have antibodies. You're giving it passive immunity, basically. You're giving those antibodies, and they will bond, and you'll get rid of those red blood cells and destroy those red blood cells, and your immune system will never even know that they were present, so therefore you never develop memory cells against them, and so therefore you don't have a problem with subsequent pregnancies with the Rh positive fetus. And so that is the fourth section. So we just have one last section here that is about disease. And so in the immune system, some things going on with the immune system, exaggerated, like a super sensitive immune system, self-directed or diminished immune responses can cause different diseases. So if the delicate balance of the immune system is disrupted, effects range from minor to often being fatal. So allergies is one example of an exaggerated or super hypersensitive immune system. It's a response to antigens called allergens. Hence, you have allergies if you're sensitive to these allergens. And so an allergen could be anything. And so it can be, example, like pollen. So people who have hay fever, localized allergies, affects just the respiratory system, such as hay fever. These guys here are just a special kind of antibody. You don't have to memorize those. Produced after first exposure to an allergen attached to receptors on mast cells. Mast cells, remember, are part of, they contain histamine, and we're part of the inflammatory response. Remember that from the innate immune system? And so then what happens is the next time the allergen enters the body, it binds to mast cell associated IgE molecules. That is, again, a type of antibody. Then the mast cells release histamine and other mediators that cause vascular changes leading to typical allergy symptoms. And so those allergy symptoms are sneezing, runny nose, watery eyes, it's an S. And vascular changes, remember, dilation. Remember that one, that histamine causes the blood vessels to dilate and become leaky. And so that leakiness creates the more runny nose because fluids are leaking out of the blood vessels, the capillaries, into the extracellular fluids are surrounding your cells of your respiratory system, and so that triggers sneezing and your runny nose and your eyes are more watery. And so let's look at this picture that describes this. So here's your IgE molecule. So let's write some things about this. I'm going to write things about this. So what happens is these are antibodies. So the first time first exposure to an allergen, this is what happens. And so these antibodies are produced in response to the allergen bind to the mast cells. So that's what you see here. So these guys here, this is the antibodies binding to the mast cell. So normally you would not have these bound to the mast cells. And these are little granules that contain histamine. So then what happens is, let's look here, this picture. So once you're exposed the second time to the allergen, so I'm going to put your second exposure. All right, a couple of things happen. The allergen binds to the antibodies bound to the mast cells. So that's what we see here. They're binding, the allergen is binding to those antibodies. Now, if you notice here, notice that this allergen is bound to one leg or one arm of the antibody here and one here. They call that cross-linking, and that's really important. So let's look here, cross-linking of adjacent antibodies trigger release of histamine. And so that's what we see here, the histamine coming out here. And so then what does histamine do? What does histamine cause? Just a review from the inflammatory response. Histamine causes dilation of the capillaries, and increased leakiness of capillaries. And so you get the normal allergic reaction. Now, some people have a super hypersensitive reaction to a particular allergen. And this can, so they call this an acute allergic response. And this can lead to what's called anaphylactic shock. It can be very life-threatening, a life-threatening reaction that can occur within seconds of allergen exposure. And so what happens here is once the allergen enters into, so instead of just the reaction being localized, like let's say in the respiratory system, let's say all around the body, the mast cells, this happens to where they release histamine and you get dilation of blood capillaries everywhere in your body. So remember what happens to dilation. In dilation is, is you go from a smaller diameter to a greater diameter. And what that does when that happens is it lowers your blood pressure. I'll just put low BP. And if that happens all throughout your whole body simultaneously, the blood pressure drops, that can send your body into shock and can cause, be life-threatening. And so that's a really big deal. People that have allergies, like for instance for allergies to peanuts is a big one. Some people have allergies to shellfish and so on, will carry something called an Epipen. I'm sure you've heard of an Epipen. Epi stands for the molecule epinephrine. Epinephrine is a natural molecule that's found and is released in our body. So these in the Epipen, you have a syringe full of it, and what it does is counteract these symptoms of anaphylactic shock. So therefore, it counteracts your allergic response. So it constricts the blood vessels, so it'll make the blood vessels go back to normal. Also, something that happens in anaphylactic shock is that the bronchioles, which are in your lungs, constrict, which makes breathing really hard. And so the epinephrine, when you take it, actually relaxes the muscles in the lungs, helping the person to breathe easier. And so that's what happens with anaphylactic shock. So if, you know, in your classrooms, if this is why you may not be able to eat peanut-related foods, because there are some people that this can happen to, and it can be life-threatening. Another thing going on with the immune system is something that's called an autoimmune disease. So in individuals with autoimmune diseases, the immune system loses tolerance for self and turns against certain molecules of the body. So some autoimmune diseases, rheumatoid arthritis is one, and so they call that RA for short. It's the autoimmune disease leading to damage and inflammation of your joints. And so for this, it's very painful, and using, you know, their joints and bending fingers and stuff like that, their immune system is attacking their own body instead of just attacking outside particles. Some other examples is systemic lupus. You've heard of it, just oftentimes called lupus. You may have heard of that. These guys have antibodies against histones, that's proteins, and DNA that is released by broken up cells, by the normal breakdown of body cells. Multiple sclerosis, you've probably heard as MS. These guys, they make antibodies against the myelin sheath, which we're going to learn in the next chapter that's in neurons, and so in their own neurons. So they're attacking that against their neurons, and we'll see that the myelin sheath is instrumental in neurons being able to transmit information from one neuron to the next. Another autoimmune disease is insulin-dependent diabetes. So this is type 1 diabetes. Insulin-dependent is type 1, and these guys have antibodies that attack the beta cells in the pancreas that produce insulin. And so therefore can't get sugar, the glucose, into their cells. And so these are all examples of autoimmune diseases. It's interesting because these autoimmune diseases, it's found that especially rheumatoid arthritis and lupus are found overwhelmingly more often in females than males. And so it's an area of big research in terms of why that is. And they also found that now there's a higher incidences of autoimmune diseases than there used to be. And so there's a lot of research going into why that is, and if it's something in our environment or something that we're exposed to or whatever, about why there's increased incidences and happens more often in women than men. And then we have immunodeficiency disease. This immuno is referring to the immune system, and so your immune system is deficient and therefore causes a particular disease. So there's inborn, or what we call primary immunodeficiency. That is, inborn means it's genetic, or there's some kind of developmental defect that results from defects that prevent proper functioning of your different types of immune systems: innate, humoral, and or cell-mediated. And then the second one is acquired. So this is or secondary immunodeficiency. So your immune system becomes deficient after you're born, sometime within your lifetime. So example of a primary or inborn, or we just wrote genetic, is severe combined immunodeficiency, where in this case both the humoral and the cell-mediated branches of acquired immunity fail to function. This is a really big deal because that really means that basically, let's go back here a couple of pages, your whole acquired immunity, which is where you can build up your memory cells and so on. So humoral, remember, is with your B cells. Cell-mediated is with your T cells. None of that is working. So therefore, they don't make antibodies, they don't make memory cells, and so on. And so people with this basically have to live kind of like in a bubble where they don't come into contact with things because they don't have the immune system. They're basically, their immune system doesn't function, and so it can be a really big deal. Things that the rest of us can fight up against, they cannot. And so that's an example of that. So that's one thing. The second was the acquired immunodeficiency. These range from temporary states, so you can have temporary deficiencies in your immune system, to all the way to chronic diseases where you have an issue with immunodeficiency for your life. So let's look at one of these. The temporary state is stress. Stress would be it's temporary. So you can have times where you have temporary situations where you are stressed. And there is evidence that shows that physical and emotional stress, either or, can harm immunity and therefore suppress or lower your immune system. So getting and being stress-free actually can help keep you healthy. They've done research where people even sleep. They've done research where adults that get less than 7 hours of sleep get sick 3 times as often when exposed to a cold virus than those that got at least 8 hours of sleep. So there's evidence between sleep and your immune system as well. So those are things that are temporary and can be reversed. The second thing is the chronic diseases. So if we flip our sheet over here, AIDS, acquired immunodeficiency syndrome. It has the word immunodeficiency in it. This is something that we acquire, or some people acquire during their lifetime from a virus, the HIV virus. So people with AIDS are highly susceptible to opportunistic infections and cancers that take advantage of an immune system in collapse. So HIV is going to affect the immune system. So because AIDS, which is the disease that is caused by the infection by the HIV virus, because AIDS arises from loss of helper T cells, and impairs both the humoral and cell-mediated immune responses. Let's go back to that same diagram here. And so what we're saying here is the HIV virus affects the helper T cells. Remember what the helper T cells do is they activate B cells to then divide and differentiate to make memory B and the plasma cells that are going to secrete antibodies to fight the pathogen. So if helper T cells don't work, you're not going to have this humoral section. And then the helper T cells also activate the cytotoxic T cells, which then divide and differentiate to make the active cytotoxic T cells that are going to kill infected cells as well as build memory cells. So none of that's happening, and then you won't have also the helper T cells dividing and differentiating to make memory cells of those either. And so basically this acquired immunity part of your immune system isn't working. So that is a really big deal. So the loss of helper T cells results from infection by that HIV, the human immunodeficiency virus. And basically, because of what we just talked about, somebody who dies of AIDS usually dies of actually something else, like pneumonia or something like that, because their immune system, these helper T cells, can't work. So their immune system is not working to fight off that infection, and they end up dying from it. And that's because of the loss of those helper T cells. So this is a worldwide problem, and so they found that the best approach for slowing the spread of the HIV virus is to educate people about practices that transmit the virus, so that if somebody knows how the virus is transmitted, you can reduce those behaviors and therefore prevent the spread of the disease. And so that is an example of more of a chronic disease that is acquired immunodeficiency or secondary immunodeficiency. All right, and that is the immune system.